Hello, this is the Code Critics. In this episode, we are going to look at generators, how they compare to iterables, iterators and sequences, and how to use them effectively. If you haven't watched our video on iterators, I suggest you watch that one first, and possibly also the one about list comprehensions. Let us quickly recap the differences between iterables, iterators, generators and sequences. Here a simplified class diagram. Iterables are at the top and characterized by having an __iter___ method. Any object with an iter method is an iterable and can be placed in a loop to iterate over its elements. Lists, for instance, are iterables. The iter method returns an iterator object, which has two methods. The iter method again, which returns the object itself, and an __next___ method that is used to retrieve the next element from the iterator. For instance, if you open a file, you get an iterator over the lines in the file back. The iterator class has two subclasses, generators and sequences. Since they are subclasses, they both have the iter and the next method of the iterator and can be iterated over. Generators have additional methods such as send and throw, which are used in the context of coroutines and are rarely used in data science projects. We will not discuss them here. Sequences have methods to get the length of a sequence and to retrieve items from a specific position of the sequence. Lists, for instance, are iterables, iterators and sequences, since lists have a length and can be indexed. Let us have a closer look at the differences between these classes. Here we create a range object R, a list L, an iterator I over list L, and a generator G. More about the generator syntax later. We can use getSizeOf of the sys library to compute the size of an object in bytes. And we can use hasAttribute to check which methods are supported by an object. Here a table where we compare the size, attributes and class of the objects and whether they are lazy or not. Range is interesting. It has a len method and therefore is a sequence. But its size is only 48 bytes, the stub byte being a range over 1000 numbers. This tells us that the range is lazy. The 1000 numbers are not created when the range object is created, but are computed on demand. Sequences are usually not lazy, but range is an exception. For comparison, see the list object. Its size is over 8000 bytes, indicating that the 1000 elements of the list are created when the list is created. So lists are sequences, since they have a len method, but they are not lazy. If we create an iterator over the list, we can see that the size of the iterator object is again only 48 bytes, too small to store 1000 numbers, and the iterators are therefore lazy. Regardless how large the list is, the iterator object will be of constant small size. Generator objects are slightly bigger than iterators, but lazy, and therefore constant in size as well. Generators provide an easy way to create iterators. We will compare a non-lazy or eager implementation with an iterator or a generator implementation next. This toy example computes the absolute numbers for a given list of numbers and also removes all zeros of that list. It simply iterates over the numbers of the list, and if the number n is not 0, it appends its absolute value to a new list, abs_nums, which is returned at the end of the function. This could be written much shorter using a list comprehension. Here the implementation. If we run either of the two implementations for a list of numbers, we get the expected result. Zeros have been removed and all numbers are positive. Note that these two implementations are eager or non-lazy. When the function is called, all numbers are computed. In many cases this is fine, but what if we need only the first, let's say, 3 absolute numbers? If the input list is very large, we would waste a lot of unnecessary computation. In data pre-processing pipelines, this is a fairly common case, especially when building a new pre-processing pipeline where we want to try different pre-processing functions on smaller data sizes first. In this case, a lazy implementation that only computes the data that is needed is extremely useful. However, if we try to implement a lazy iterator that computes the absolute numbers while filtering out zeros, we end up with this rather complex and lengthy implementation. Generators allow us to do the same with much less code. If you compare this generator function with the eager implementation, you see that there are only 2 differences. Return has been replaced by yield, and we don't create a new list with the absolute numbers anymore. Any function that contains a yield statement is a generator, and a generator is simply an easy way to create an iterator. Similar to a list comprehension, there is a generator expression, with the only difference that round brackets instead of rectangular brackets are used. The generator expression, however, is lazy, while the list comprehension is eager. The generator allows us to collect just the first 3 absolute numbers by calling next 3 times on the generator, without having to compute the absolutes of all numbers in a potentially very large input list. A more interesting and common use case for generators is the flattening of large nested data structures. For instance, a nested list. Here, an eager implementation without the usage of generators. First, we check if the input xs to flatten is a list, and if so, we recursively call flatten for each element of the list and append the returned list to the flat variable. If the input to flatten is not a list, we wrap it in a list and return. If we invoke the flatten function on nested list, we get back a flattened list. As mentioned, this implementation does not use generators and is eager. Even if we only need the first few elements flattened, this implementation has to process the entire input list. Here now the lazy implementation using generators. The first thing you will notice is that the code is shorter, since we don't need the temporary flat variable anymore to accumulate the flattened list. Secondly, you see that the return statements have been replaced by yield, making this function a generator. 2 other details are of special interest. Note that we need an else statement, since yield, in contrast to return, does not exit the function. It only yields an element and the generator code continues after the yield. Secondly, the recursive call of flatten returns a generator, and we can use yield from to yield elements from this generator. That saves us an extra for loop that would iterate over the elements the generator returns. A generator, while compact, can describe complex behaviors with multiple yields and recursive calls. If we define a little helper function take, we can use it to retrieve the first 3 elements of the flattened list. As a last example, let us look at a slightly more complex code that finds all words in a set of files that contains a given query string. Here the implementation. We use glob to extract all file paths that match a given pattern. For each file path, we open the corresponding file, iterate over its lines, and split each line into words. If the query string is part of the word, we yield the word. This is an efficient implementation that allows us to find matching words in multiple files, a bit like grep. The biggest drawback of this implementation are the deeply nested loops. If we want to add additional functionality, such as returning the file names and the line numbers where matching words were found, the code would become unpleasantly complex. Let us decompose this code into manageable pieces. First, we write a function that returns the sequence of file paths using glob. Secondly, we implement a generator that opens the files and yields all lines from all files. Note the usage of yield from, which makes the lines function a generator. Thirdly, we write another generator that yields all words of a line. Again, we use yield from. Finally, we implement the find function. In the first line, we simply chain all the generators, which gives us the generator over all words in all lines in all files. In the second line, we use a generator expression to filter for words that contain the query string. While the decomposed code is longer, the individual components are simpler, can be reused, and can be extended more easily. To summarize, generators provide an easy way to implement iterators. A custom iterator requires the implementation of a class with next and iter method, while a simple yield statement converts any function to a generator. Most importantly, iterators and generators are lazy. An eager implementation of the find function shown before would extract all words from all lines from all files, even if we need only the first match. The generator, on the other hand, would perform only the operations necessary to find the first match. Generators can be chained, and the entire chain of generators or iterators is lazy, which enables the processing of data too large to fit in memory. Generators tend to make code shorter, since the accumulation of results, typically in list, is replaced by a yield statement. And finally, while generators are slower than for loops or list expressions for simple operations, for many real-world problems that involve more complex operations, generators tend to be faster overall, since they are lazy. And that's it. Thank you for listening. You will find the links in the description, and please subscribe or like.